Hey everybody, let's take a little different type of problem when it comes to Newton's second law. The formula force equals mass times acceleration, which is essentially the quintessential um, Newton's second law formula relating kind of mass and force and acceleration, can be written a little bit differently than that if we think about um force here instead being weight. Now, weight is a force. Weight is specifically the force because of gravity. Sometimes we just go ahead and say, let's call this F with a little g afterwards, like the force because of gravity. Sometimes you might see it written a little differently and say W. Sometimes we replace uh, the force due to gravity here as W. And when we do that, we often say, hey, the mass of whatever object you're talking about. And then we replace this A with a lowercase letter g. And this is important. This lowercase g does not stand for gravity per se. In fact, this lowercase letter g here is an acceleration. And that can be frustrating for a lot of people. So it is not the force of gravity that is this letter G, and it is not gravity itself. It is the acceleration because of gravity. It's this: if I was to take an object and I was to drop it and let it fall down, there would be a certain amount of force that gravity would pull downwards that we call weight. And that weight, that gravity pulling down on the object, causes this object to accelerate. And the acceleration that that object travels downward, I mean, speeding up as it falls, has a very specific number. And it turns out that all objects, regardless of their weight, actually accelerate at the same rate on Earth's surface or near Earth's surface, which is really counterintuitive. And I remember the first time I learned this, I really had to do some testing for myself in my living room. I was about your age, and I was sitting in my living room doing some physics problems, some friends, and we learned that all objects fall at the same rate. And I thought, well, that's ridiculous. How is that possible? And so we started dropping objects in the living room to see if they hit the ground at the same time. We needed objects that were about the same size and about the same kind of air resistance. And so we started dropping spherical objects like billiard balls, pool balls, and ping pong balls, which are very different than each other in weight. But it turns out that ping pong balls and pool balls actually fall and hit the ground at the exact same time. You can do a little test for yourself. This number right here is true at Earth's surface that I'm going to write in. And at Earth's surface, all objects accelerate towards the ground at 9.8 meters per second every second. That's how much they speed up their velocity every second. 9.8 meters per second every second. So after 1 second, they're traveling at 9.8 meters per second. And after 2, they're traveling at 19.6, and so on. We just add 9.8 meters per second every second, and we're good to go. So why do I mention all this? And it seems like I've written all this in the margins over here, is that this is going to help us to get going to be able to answer the question that's up above. And the question that's up above here asks this. It says, a large elephant can have a mass of 5,000 kilograms. So it's just a single piece of information that's given so far. And then it tells us a little bit later in here, it says, what does the elephant weigh in newtons? This doesn't seem like enough information to do a problem that has 3 variables. And the reason why that only 2 variables are given is that one of these variables of the 3 is well known. And that variable of the 3 is this one right here, this acceleration because of gravity, right? Meaning that it's the same for all objects. So this 9.8 meters per second squared often gets left out of problems because it is something that is true for all objects. So if you see less, kind of things here than you need, there might be something that is an actual kind of known quantity that you might need to go back and take a look at. So in this case, Here's our large elephant, and we're asking its weight. So the equation that I'm going to look at is this one right here. This is my weight is equal to mass times the acceleration due to gravity. And since I know the mass here, and the acceleration to gravity is always the same, which is this 9.8 meters per second squared, we can figure out the weight because it's the only thing left over. So let's go ahead and do this here. I'm going to put in my givens. My givens, remember, I'm putting in the connections between the numbers and then their symbols. So I'm going to go ahead and say the mass of this elephant is 5,000 kilograms. And I know that it's a mass. It says that it's a mass, and it has the unit of kilograms, so that's important. The other thing that I know, even though it's not down in the problem, is I'm going to go ahead and write down this acceleration due to gravity. So I'm going to put down G is equal to 9.8 meters per second every second. Again, not in the problem, but I'm writing it down because it is known. Now, what is the unknown? Well, the unknown is the weight. This is the thing I do not know, and so I'm trying to solve for that. We have only one equation, so let's go ahead and put that equation down that we're talking about here, and that's W equals mg. Weight is equal to mass times an acceleration because of gravity. This is Newton's second law rewritten, right, for weight. So it is Newton's second law, but rewritten for weight. So there's my equation. I'm going to then substitute in the things that I know. So I'm going to say W equals, and the mass is 5,000 kilograms, which is a lot. And then my acceleration to gravity is 9.8 meters per second every second. And so when I multiply these two numbers together, I get a sizable amount, and that amount is 49,000. What units do I get out of this? Well, I want it to be in newtons in the end. Do I? Well, a kilogram meter per second squared is also known as a newton. The newton is the derived unit of these pieces. So this is my correct amount in newton. So here's the kind of final answer to this one. The weight in newtons is 49,000. Now I have this other picture over here because this is my car. This is my amazing partner here, and we are going rock climbing on these rocks in the background that are called the feathers. And so my car, I drive a Mazda 3, and we often go traveling with it. The Mazda 3 actually has a mass, well, let's say a weight in this case, of 3,000 pounds. About 3,000 pounds to 3,200 pounds, depending on how you look at it. So 3,000 pounds is the weight of my car. And if this is the weight of my car, how many elephants, right, are equal here? So how many, maybe I should put it this way, how many cars could I add up to total up to one of these elephants? Is it more than one? Well, we need to do a little conversion here to be able to figure this out. If you were to go on Google and convert 49,000 newtons into pounds, you can do that, or you could use our conversion factors, which work out just fine. And what you'd find out is that this number is approximately 11,015 or 11,016 pounds. So this is the elephant in newtons, and this is the elephant in pounds. Now notice my car is only 3,000 pounds, and this one is 11,000 pounds. So if this number was 12,000, this number was 3,000, that means that I would get a total of 4 cars, right? So I could take 4 of these cars, and that would finally equal the mass of one of these elephants. And I have had elephants just like this one walking straight towards my car when we lived in Africa, which was pretty outstanding. The actual number, if you do a little conversion, is closer to 3 point something, 3.5 about. depending on how you look at it. But that's still pretty impressive that 3.5 of my cars equals to the total of this elephant right here. They are absolutely massive creatures. And so very cool stuff just to think about. So the weight is equal to the mass times the acceleration due to gravity, which I just plugged in the pieces. Notice it's not in the problem. And I get that 49,000 newtons. If I was to convert that, that's 11,000 pounds. And that's approximately 3.5 of my car. All right, interesting work. And I hope that this helped flow a little bit. And I'll see you in the next one. All right, adios.